Hey guys, welcome back. This is the beginning of the wave notes, which you should have already received. You should complete the wave inquiry lab prior to us going over this. So when we talk about the wave is going to be a motion of a disturbance. And it can be a disturbance up or down in the y direction or a disturbance in the x direction. Whatever the wave is traveling through, and some waves we'll find out won't need anything to travel through, but what it's traveling through is going to be the medium. And a lot of what I will show you will be things traveling through the air or through a spring or through a rope. Mechanical waves always need a medium. Examples of mechanical waves are sound and water. You might have heard the tagline, "No one hears you scream in space." This works on two levels. One, sound requires things to be vibrated. Space doesn't have anything that's vibrating, so there can't be any sound in there. And two, if a monster attacks you in space, there's not going to be anyone that's going to be able to come and help you. So the idea of this is this disturbance gets pushed through the particles, but the particles themselves aren't moving the whole distance. So the wave itself, in this case, is going sideways, but the individual particles on the rope are just going up and down. And they are propagating a wave that's perpendicular to this. So here's an example, and I'll do demonstrations of this for you guys in class. But we have what is known as a transverse wave, where we are lifting our hands up and bringing it down and creating a pulse, and this pulse is traveling sideways. If you time these pulses out perfectly, you can make it look like a sine or a cosine curve, so it can look like it is sinusoidal. There are two different types of these waves. There are transverse and longitudinal. These will be different in how they travel and the disturbance that creates them. Transverse waves, like the rope that I showed you, your disturbance is perpendicular to the motion. So we have a disturbance up and down, and our motion is to the side. On a transverse waves, we have a number of things that we can label. The maximum distance from zero is the amplitude, which they designate as lowercase a, but we've called capital A. The distance between two like points on a graph or one complete cycle is a wavelength. This is a lowercase lambda. And this is going to be measured in meters. This is going to be measured in meters. We also have a cycle, which is going to be how long it takes for one of these to happen. So a cycle is a period that's measured in seconds. And then frequency and period are related because frequency is going to be how many of these you have per second. And like I said, we usually use the one that's greater than 1. So in this case, this would be our period, and we know that we can represent our graph as x equals a cosine omega t. We also have another way to quantify how this wave is moving, and this is going to be the wave's velocity. And this is going to be equal to the wavelength, which is in meters, and the frequency, which is 1 over second. So if you look at the product of that, you're going to get meters per second, which is going to give us what the velocity is. And we're going to look at how we can change this velocity. All right, so this is a transverse wave. I am moving my hand up and down. I am creating a disturbance, and this disturbance is traveling perpendicular. A longitudinal wave has a disturbance that is parallel to how it's traveling. And so this hand is moving side to side, and we have areas where they are compressed and areas where they are stretched together. In your notes, they call this expansion. It also is known as rarefaction. And then again, our wavelength is going to be the distance between like points in our wave. So the distance between the center of the compression to the center of the compression. Sound is going to be this type of wave, which sound will be our next chapter. So here we look at a longitudinal wave, and I'll show this as a demonstration to you guys in class as well, but I can cause a disturbance where I bunch the spring together and it will move in the same direction and go on down. Now, realistically, it's hard to draw a sound wave because there's areas where the particles are closer together and then farther apart. So this shows us where, as we hit this drum and it goes out, as the drum goes back out, it pushes those particles together. And then as it comes back to rest, we have an area of it being spread and compressed and spread and compressed and spread. So typically you don't draw this as a transverse wave. Very often it's misdrawn as a transverse wave. We can relate our intensity to our power divided by our area. What's important to us is how it relates to energy. So for us, the fact that the energy is proportional to the amplitude squared is an important thing. You don't need to know there's going to be a very complicated equation here that will never show up. You just need to know this relationship. Very much like you need to know that how the period and the radius relate and elliptical orbits. And realistically, if we're looking at a sound wave is not going to be exactly like a spring, because when you talk, it doesn't just go in one direction. We're going to see that there's a lot of reasons why waves and particles have differences, and this is one of them. So when I talk, the sound is going to go out. It goes out in all directions. So we have this sphere of areas of compression and rarefaction that are going in all directions. I kind of think about it as, if you guys remember the Justice League, but when Aquaman is summoning all the animals in the ocean, and he sends out the thing and it radiates out in all directions from him to get there. In this case, the energy is proportional to 1 over r squared. Which we're going to see this shows up a lot. So this would be an inverse square relationship. Inverse square relationship. And this is the equation I don't want you to worry about. What do we need to know? These two things. Energy is directly proportional to the amplitude squared. Energy is inversely proportional to the radius squared, where this is the amplitude and this is how far you are from the scene of it. This will never show up for you guys, I promise. All right, so looking at our wave speed equals frequency times wavelength, we can do a couple of simple calculations with this. This will be easier for you to look at the notes I passed out. It'll be hard to see the printing on this because it's a copy of a PDF. But a piano string vibrates with a frequency of 264 hertz. If the sound wave has a wavelength of 1.3 meters, what is the speed of sound in air? So our velocity is going to be this frequency times wavelength. So this is going to be 264 times 1.3. And again, this is 1 over seconds. So 1 over seconds times meters. And it looks like for this one, it's going to be 343 meters per second. Again, sound is the next section that I kind of put with waves and sound together. So that'll be our next test. And we'll talk about the speed of sound and how it changes. The largest reliably measured depth of the Pacific Ocean is about 1.09 times 10 to the 4th meters. How many wavelengths of sound waves of a frequency of 2.5 times 10 to the 2nd hertz would fit in this distance? The speed of sound in C is about 1,530. So very different from what we calculated previously. All right, so I need to know what my wavelength is. So it's 6.12 meters. That's nowhere near what our answer is, but they're telling us they want to know how many would fit in this distance. So I'm going to take this divided by my 6.12. And I have 1781. Cicadas produce a sound that has a frequency of 123 hertz. What is the wavelength of this sound in air? The speed of sound in air is 334. So again, wavelength would be our velocity over our frequency. So I'm going to have 334 divided by 123. And so I get the 2.7. Human fingers are very sensitive, detecting vibrations with amplitudes as low as 2 times 10 to the negative 5th meters. Consider a sound wave with a wavelength exactly 1,000 times greater than the lowest amplitude detectable by fingers. What is this wave's frequency? Would it be audible to the human ear? So we're saying that our wavelength, our wavelength is 2 times 10 to the negative 5th times 1,000. So that would be 2 times 10 to the negative 2nd. My frequency is going to be equal to my velocity divided by my wavelength. I'm going to use the speed of sound from the previous problem because they don't give us one. And again, if you're not sure, you can look at our units. And I got 16,700 hertz, which would be audible, which we haven't learned yet, but that doesn't show up. The highest pitch sound that a human ear can detect is about 21,000 hertz, and we'll talk about how that changes. On the other hand, dolphins can hear ultrasound with frequencies up to 280 kilohertz. What is the speed of sound in water if the wavelength of ultrasound with a frequency of 2.8 times 10 to the fifth hertz is 0.51 centimeters? How long would it take this sound wave to travel to a dolphin 3 kilometers away? So first, our velocity is going to be our frequency times wavelength. We're saying that our frequency is 2.8 times 10 to the fifth hertz. And we're saying that our wavelength is 0.51 centimeters, which would be 0.0051 meters. So I have a velocity of 1428 meters per second. We have a dolphin that is 3,000 meters away. The speed is going to be essentially constant. So we have 3,000 divided by 1428. Which is 2.1 seconds. 19th century fisherman's cottage in England is only 2.54 meters long. Suppose a fisherman whistles inside the cottage, producing a note that has a wavelength that exactly matches the length of the house. What is the whistle's frequency? The speed of sound in air is 334 meters per second. All right, so I'm going to say that velocity equals frequency times wavelength. Frequency is going to be equal to velocity over wavelength. So I have 334 divided by the 2.54 meters. I have 131 hertz. Number 6, the lowest vocal note in the classical repertoire is low D, frequency of 73.4 hertz, which occurs in an aria in Mozart's opera. You're not going to get me to try to say that. If low D is a wavelength of 4.5 meters, what is the speed of sound in air? So our velocity is going to be equal to frequency times wavelength. Oh, did not mean to do that. So this is going to be 73.4 hertz times 4.5 meters. So 330 I got. And again, I'll talk to you guys about how this varies meters per second, depending on different factors, because that will be important in the next chapter.